Okay, for tomorrow, actually I've set up in the folders for tomorrow, Wednesday, and Thursday. I have obviously the reading assignments are there, but also there are videos and there's some problems we'll do either as practice or we'll do in class. So everything's set up for the next 3 days. But for today, we just had a couple things that I want to go through, and the one thing you'll see for tomorrow is a lot of the material tomorrow is on epoxidations and opening up epoxides, which hopefully you were just able to do. So that should be pretty straightforward, along with those problems in Top Hat. But we may do just a couple of those. Okay, so one of the things that we kind of left off last week before was the oxidation of alcohols. And Top Hat doesn't show all the reagents of alcohols. Particularly, we're going to break these down into two classes. So when we talk about oxidizing an alcohol, we're going to be oxidizing the carbon up to a carbonyl. So again, this is a loss of hydrogen in the oxidation. So if we're looking at oxidizing the alcohols, we have to break these down into primary and secondary. So if we have a primary alcohol, we then have one alkyl group attached, and we're going to form either an aldehyde, or we're going to continue on to the carboxylic acid. And then when we talked about reductions, we talked about reducing the aldehyde or the carboxylic acid all the way back down to the primary alcohol. We didn't take a carboxylic acid and reduce it to the aldehyde. You can't do that. It's all or nothing. You either take the carboxylic acid and leave it as is, or you take it all the way down to the primary alcohol. Now, in the future, there's going to be ways to do that, but not today. So, in terms of oxidation, there's going to be two sets of reagents that we can use. One that will take us to the aldehyde and stop, and the other which will take us all the way to the carboxylic acid, which means that what it first does is it makes an aldehyde, then it oxidizes the aldehyde to the carboxylic acid. So that's the two classifications of reagents. And these are either going to be what we call strong oxidizers, which will take the primary all the way to the carboxylic acid, or we're going to have weak oxidizers, and the reason that they were developed was to stop at the aldehyde specifically. So there's really no other way. Those reagents were developed specifically for that reaction. So that's going to be how they break down. And fortunately then, the other alcohol that we're going to oxidize is the secondary alcohol. And if you think about having a secondary alcohol that you're going to go ahead and oxidize, all it can go to is the ketone. And in this case, the reagents we're going to talk about, either the strong or the weak oxidizers, either one of those, Either the strong or the weak oxidizers will go to a ketone. So in this case, there's no two sets of reagents, it's just one. So what we have to do is we have to list then the strong oxidizers and the weak oxidizers. So in terms of looking at the strong oxidizers, there's a whole list of these things. We could use potassium permanganate. We could use any chromium 6 reagent, and that includes potassium dichromate. It involves taking chromium trioxide and mixing it with sulfuric acid. That's sometimes called the Jones reagent. Is chromium trioxide with sulfuric. Sometimes you can even have hydrogen peroxide used, or even oxygen gas will oxidize certain things. So this would be our list. Our primary list here is going to be our potassium permanganate and our chromium. Those are going to be the big reagents that we use. So those are the primary ones. And environmentally friendly wise, hydrogen peroxide and oxygen would be the best, but chromium trioxide is not particularly environmentally friendly. Anybody seen the movie Erin Brockovich? Yeah, see, this is Erin Brockovich was a fairly popular movie back in the day. Apparently not your day, but that's with Julia Roberts. It's about lawyers, but there was an environmental issue that was behind it. So one of the issue about that was that they used chromium 6 reagents. Sometimes, either chromium 6 or chromium 3 in terms of stopping corrosion of pipes. When you have water flowing through pipes, like drinking water has to have phosphate in the water going through the pipes, or you end up like Flint. The reason that Flint happened was because they didn't add the phosphate, or the phosphate wasn't effective. And so normally in a pipe for drinking water, it's the inside of it is coated with like calcium salts, which are perfectly fine. That's the hardness of the water. And you add phosphate, like if I go to the drinking fountain, it'll have about 1/4 of a part per million of phosphate in it, because what that does is that combines with any calcium and it creates basically the coating, or it keeps the water a little bit basic so that it doesn't become acidic. What happens when it becomes acidic? It starts to strip off that calcium layer on the inside of the tube, or inside of the pipe. And then eventually you get to the old lead pipes. If there's nothing there to protect the lead, then all of a sudden the lead gets leached out into the drinking water, which is what happened in Flint. Their water was too acidic, they didn't have any of the corrosion inhibitors, and so they basically stripped off the entire inside protective coating of the pipe, and the lead concentrations went absolutely berserk. In an industrial setting, they'll use chromium 3, chromium 6. It's a closed system, so you're not drinking it, but they'll keep it in order to stop the corrosion of the pipes. So what happened is that some of that escaped, went into the groundwater, and then people were drinking it. Chromium 6 is actually orange. In the movie, they showed a pond which was green, which is chromium 3. But the issue is chromium-3, could it be reoxidized to chromium-6 at some point? So anyway, there was some evil company that did that, and the lawyers wouldn't take it on, so she was a legal aid, so she took it on, and I think she's now a lawyer. She shows up occasionally whenever there's environmental issues, because they won, I don't know, tens of millions of dollars. They've got a lot from that company. So the issue in Erin Brockovich was chromium-6. So we wouldn't necessarily use this in a synthesis, or again, we'd have to show our drug regulator that we've gotten all the chromium-6 out, that we didn't leave any other chromium in there because it could oxidize in the body. So it's not as popular as it once was, but it works very efficiently. CaMNO4, probably a little bit better. And so any of these strong reagents will oxidize primary and secondary alcohols to carboxylic acids and to ketones. The issue is, what if you want to stop at an aldehyde? So if you want to stop a primary from oxidizing all the way, and you just want to make an aldehyde out of it, and in this chapter, there's only one reagent that they introduce. And then they say, well, in chapter 22, we'll introduce 2 more. So I'll introduce 1. And the principle here is that if chromium-6 oxidizes all the way to the carboxylic acid, can I kill the chromium-6? Can I poison it? It's sort of like the Lindlar catalyst approach. So what they found was, I believe this was a famous synthesis, or famous organic synthesis person at Harvard called E.J. Corey. I think this is actually called the Corey-Suggs reagent. And I think it's the same Suggs that when I was a postdoc at Brown, he was a professor there. But what they do is they add pyridine, which is the 6-membered ring with a nitrogen in it. It is nasty stuff. It's a reproductive hazard for men. It has a gender-specific action. We put a hydrogen on there, so we make pyridinium. And then we add, well, what we added was HCl to turn the pyridine into pyridinium. And then we add the chromate. So this is called pyridinium chlorochromate, which is abbreviated as PCC. There's also pyridinium dichromate, I believe, PDC. But they're all basically a poisoned chromium reagent. And so if you want to stop at the aldehyde, PCC is the reagent to use. Anything other than PCC right now is going to take that all the way to the carboxylic acid. So that's the only one. There's also another one that is called Swern, that's much more environmentally friendly. And then there's also Des-Martin periodate, which is, I think, a little bit more, and it works pretty well. I've had a student use that in the past. And the only issue there was gently shaking the separatory funnel and then not having it spray stuff all over the place, which is what happened the first time it got used. So if you take it easy on that, it works pretty well. So there are more environmentally friendly reagents other than PCC. But PCC, and that's the reagent I would give you, I just say PCC, that's all you have to say. That specific purpose is to make aldehydes and stop. That's all it does. Now, if you reacted PCC with a secondary alcohol, it'll go to the ketone. So it can be used either place. But it stops at the aldehyde. That's it. So that makes it pretty easy because you don't have to remember the other reagents. There's just one for the moment. So that's what the oxidation of the alcohols involves. So if I said, for instance, I want to take this primary alcohol and I want to form a carboxylic acid out of it. You could say any of those reagents. You could say, well, I'll use KMNO4, I'll use chromium trioxide sulfuric acid, or I'll use potassium dichromate. Any of them will work. If you want to stop, if you say I want to stop at the aldehyde, then you would just use PCC. Now, aldehydes can be oxidized by any of the harsh reagents as well as some of the milder ones. So if you said either oxygen or hydrogen peroxide would actually take an aldehyde up to a carboxylic acid, but they tend to react slower. So, I mean, if you make wine, or I suppose any alcoholic beverage, you have to protect it from oxygen. Because any of the aldehydes that are in there, well, the alcohol that's in there, you don't want the ethanol that's in your alcoholic beverage to be oxidized to an aldehyde from oxygen gas. And you certainly don't want it oxidized further to form a carboxylic acid, or your bottle of wine is going to be a nice, expensive bottle of vinegar, because acetic acid is vinegar. So you have to protect it from just simply O2. We'll oxidize it. And sometimes when we go downstairs and we want to get an aldehyde, a bottle of an aldehyde, we'll see that the aldehyde bottle is like half solid, half liquid. And the solid is actually the aldehyde that's oxidized over time into carboxylic acids, because once you form a carboxylic acid, it can hydrogen bond with itself, and so it becomes a solid. So normally when we have an aldehyde, we have to purify it from the carboxylic acid by reacting it with sodium bicarbonate. The sodium bicarbonate deprotonates the carboxylic acid, makes it an ion. It goes into the aqueous solution, and then we distill off the aldehyde and keep it away from oxygen. So the aldehyde is particularly sensitive, and you've got to keep it away from oxygen, because over time it will react. But you could use something environmentally friendly like hydrogen peroxide if you want to do those oxidations as well. So you don't necessarily have to use the harsh chromiums, but they work well. So that's sort of the oxidation scheme. That's the opposite of the reduction scheme. So I didn't go over that on Thursday, so I didn't put that on today's exam. Does that kind of make sense? So those are the reagents you have to remember for oxidation. Then the other issue, which sort of ties in with what the topics that for today would be, are converting OH groups into good leaving groups. So here's how I set up that discussion. You have that alcohol. And I would like you to make either one of those two products. But we'd like to be able to make one way and the other another way. So what could I use? To make which one? So you want to use NH2 minus to make the top one. What do you want to use to make the bottom one? What's his issue? The OH? That's a good question. Would NH2 minus deprotonate the OH instead of forming the double bond? That would be a way around it. Yes, and ultimately no for the answers for that. So yes, NH2 minus would deprotonate the OH. And what would happen? Well, okay, so NH2 minus is going to end up deprotonating the OH. So we are not going to make that product. We are going to make that. And down here, what's going to happen? You could say, but tertiary butoxide, what it'll end up doing is forming an equilibrium where it deprotonates that OH minor, or that OH. So neither one of these is going to work, but that's okay. Because if I had to guess, or this is the reason why I set it up this way. So I can trap people into thinking, oh, we'll just use NH2 minus and tertiary butoxide, which we will, but not with alcohols. So we do have this choice, but not with alcohols. And if we try and use a strong base with an alcohol, all I'm going to do is deprotonate it. Okay. Now we could go back and we could say, what did we use? What functional group over here did we react with NH2 minus and tertiary butoxide to make alkenes? It wasn't an alcohol. It was what kind of molecule? What did we use? I'm waiting. What goes here? An OH? No. What else could I put there? What? Chlorine or bromine? So in other words, halogens. So I can use this method to make these two alkenes by using an alkyl halide. But I can't do it with an alcohol, although that's not true. Because I could have taken this alcohol and made the most substituted alkene out of it by using something and heat. It's got to be an H plus. I can use H2SO4, H3PO4 in heat. Why do we use H2SO4? Because it's got a lousy, its conjugate base is a lousy nucleophile. So all it did was protonate the OH and make it leave. So if I can convert an alcohol to an alkyl halide, then I can use potassium tertiary butoxide or the NH2 minus and choose my alkene, but I got to turn an OH into a halogen. So how do I do that? I want to do a substitution reaction. I want to substitute the OH with a halogen. So what should I do? The first thing I need is I want to make the OH leave. So use H plus. So I need to make the OH leave, so I need an H plus. Now I want to replace once I protonate that OH, it becomes a water molecule. I want to substitute the chlorine for the water molecule, so how about I just use HCl? Use HCl, turn the OH into water, have the chlorine come in either by SN1 or SN2, and do the substitution. Well, I'm coming back to that. Because you said, well, let's just add H plus to it. I'm going to, and you're going to tell me what happens. Alex? What? Sure? So the whole issue is that these will deprotonate an alcohol. The strong bases will deprotonate an alcohol. So what I need to do is I need to turn the alcohol into a leaving group. How have I been doing that? By adding H plus to turn it into water, right? So that's been our approach. We just say, well, let's add H plus to the OH, and we'll make an oxonium ion, and then the oxonium ion basically is a water molecule. It's going to leave either SN1 or SN2 with potential rearrangements. Now, what if I add the What if I make the oxonium ion and then I say, oh, let's add NH2 minus to it? What's going to happen? It's just going to deprotonate the oxonium ion. So the issue is, if you want to make an OH group leave, you can't use a basic reagent. Because the way we've been making OH leave is by using acid. If I dump acid in there and then I put in my basic reagent, all I'm going to do is deprotonate. I'm not ever going to actually substitute, and I'm not actually going to do E2. Because remember, this does E2. So we can't have any acids in the reaction. So then we just say, great, turn this OH into a chloride and then do your reactions. Which works if we know the reagents. So HCl works, but it has some issues. It could rearrange. Primary alcohols, you guys didn't do this experiment, you didn't do the experiment last in Organic 1 lab, but in the past when we've tried to convert something like butyl alcohol into butyl chloride, we've added the equivalent of HCl to that, and we've added heat, and we basically have done a reflux, which you guys didn't do either, which is basically boiling the solution for 45 minutes, and you get an okay yield. So converting primary alcohols to chlorides with HCl isn't all that efficient. This one up here could undergo rearrangement. So there's some other reagents we should probably think about if I'm going to convert an OH to a Cl. Right? We have two. So if I want to take an alcohol and I want to convert it to an alkyl halide, my first choice would be to use Pcl3. There's a Pcl5, so that's phosphorus trichloride or phosphorus pentachloride. That works pretty well. Or you can use SOCl2, which is called thionyl chloride. That one also works fairly well. So that's the purpose. There are some reagents that only have one purpose. Okay? PCC a minute ago, PCC oxidizes a primary alcohol to an aldehyde. That's its purpose. That's all it does. We've seen, like hydrogen peroxide, many purposes, depending on the reagents. But the PCC, its purpose is to make an aldehyde. Pcl3, Pcl5, thionyl chloride, their job is to turn an OH group into a chloride. That's their job. So much so that we're going to talk about making an alcohol into, a carboxylic acid into a acid chloride. We've already talked about using the acid chlorides with Grignards. Well, where does the acid chloride come from? It comes from reacting a carboxylic acid with, I want to convert an OH to a Cl, so you could react the acid with thionyl chloride or like Pcl3. So again, that's its job. convert OH to Cl. For an alcohol, but it also works for carboxylic acid. So once you convert the OH to the Cl, then you can use NH2 minus or tertiary butoxide and go ahead and do those reactions. Do the E2 reactions. Because you've eliminated the OH as an acid. So that's one way to do those reactions. The other way is to convert an alcohol by reacting it with a reagent that looks something like this. We've got an S double bond O with a Cl. And this one particularly, this is called tosyl chloride. There's also just an S double bond O, two double bonds O with a Cl with a CF3. This is called a triflate, or it forms a triflate. It's trifluorosulfonyl chloride. And then there's also, you can just use a simple methyl group. And the book talks about all three of these. My favorite is just using tosyl chloride. Yeah, triflates are great, but they have a tendency to react with any and all OH groups, or any and all oxygens. Whereas the tosyl chloride is a little more controlled. So here's what happens. You react the tosyl chloride with an alcohol, you're going to eliminate HCl, and you're going to make what's called a tosylate ester. So the tosylate ester is basically, it's an ester in terms of being S double bonded O's with an O and an R. So it's a sulfur-based ester. This group, this comes from a toluene, which we'll learn about in the future. So we can make a tosylate ester. So the alcohol reacts with the tosyl chloride to make a tosylate ester. Now what I've actually done then is I've turned the OH into the tosylate group. The tosylate group is an outstanding leaving group. Because if I took something like a chloride, the chloride would come in, react with the carbon, and it would kick off that group, and it would make this, that would be your leaving group, would be the tosylate group. And why is the tosylate group an excellent leaving group? Well, what makes an excellent leaving group? Something that is a poor let's go back to the beginning. Leaving group abilities based on one thing. Basicity inversely. Leaving group abilities based on basicity. Poor bases, great leaving group. Strong bases, like OH, lousy leaving groups. This is the first time I've said that in this class. I don't know. I said it a lot in the last one. So, leaving groupability based on one thing, inverse of basicity. So that must mean that this tosylate is a terrible base. Why is it a terrible base? There's my acid-base equilibrium. What can I do to push that equilibrium towards the right? Because the more this dissociates, the stronger the acid, the weaker the conjugate base. So how do I get the equilibrium to push to the right? How do we normally push equilibria to the right or left? Using what principle? It's French. It means the Chatelier's. Le Chatelier's principle, except here the Chatelier's principle doesn't work. Because if I add more HA, I'm going to get the same percentage of H plus and A minus. So what do I do to push this equilibrium to the right? I make this more the more stable I can make the conjugate base, the more the equilibrium will push to the right. Again, I think this is the first time we're doing this in this class as well, but I did it before. So, for any kind of equilibrium, yes, Le Chatelier's principle will work, but only if there's two things on both sides of the arrows. If there's only one, Le Chatelier isn't going to work. I mean, it could work if you remove something. But in this case, what I'm going to do is I'm going to say, you know what, the more stable I make the conjugate base, the more the equilibrium is going to push to the right. So why is this stable? Why is that a stable anion? Because of resonance. So this is an even better leaving group than like an iodine. So let's take a step back. So yes, if I want to do E2 reactions of alcohols, and also SN2 reactions of alcohols. So if I want to take my alcohol and I either want to do an E2 reaction to form a carbon-carbon double bond, or do I want to do an SN2 reaction to replace that OH with some other group, I need to convert the alcohol into a good leaving group. In the past, we've used acid. Acid's not compatible with any of our strong bases. So for E2, H+, not an option. Down here, H+, too slow. So I can convert my alcohol to a chloride if I use Pcl3 or SOCl2. That would be great. Or the better way would be to take or another way, I guess, is to take your alcohol and react it with your tosyl chloride. And if you react it with tosyl chloride, what you end up doing is you end up then forming the tosylate ester with the ring and the CH3. And now this is a good leaving group. And so now I can do E2s, I can do SN2s. And there are advantages to using tosylate ester as well as using chloride. If I use a tosylate ester, then I don't have to worry about potentially doing any rearrangements. But now I've converted OH into a good leaving group. So that's where our E2, it's got to be done that way. You've got to convert OH into a chloride or a tosylate ester, either one. So that's what we need to do now. Now there are a couple things there is a stereochemical issue that can be dealt with. So if you had, for instance, an enantiomer, if you had the enantiomer of the alcohol and you wanted to convert it to a chloride, in this case, we have an issue. How do I want the stereochemistry of the final product? Do I want it So if you're going to turn that OH group into a chloride, it would be helpful if we had a way to control the stereochemistry so that I could turn that OH into either invert retain the configuration or make it 50-50. Now the SOCl2 retains the configuration. And the mechanism is in the book. I'm not concerned about the mechanism. SOCl2 though will retain the configuration. How do you think we make 50-50? When do we make 50-50? We need a carbocation. So how am I going to convert the OH up here into a carbocation? How do I make the OH leave? Just add HCl, because the H plus is going to protonate the OH. It's going to leave. I'm going to end up with a carbocation, and then the chloride's going to react on both sides to make this 50-50. And that's what the squiggly line means. The squiggly line means you've got 50-50. So force it to go through there. How would I do inversion, though? Inversion of configuration means what kind of mechanism? An SN2 mechanism. So I need to convert the OH group into a leaving group that will then undergo SN2. So how do I convert the OH into a leaving group? Turn it into a react it with tosyl chloride, so react it with the Cl, with the S with two O's, and then the benzene ring, and then the CH3. First of all, react it with tosyl chloride to convert that OH group into a tosyl ester, which is going to have the same, nothing's going to happen to the chiral center. So I'm just going to convert the OH into the tosylate ester. Now react it with chloride. Chloride comes in, kicks it off, and since that is an SN2 reaction, I'm going to end up with inversion of configuration on the chloride. So first step, tosyl chloride. Second step, add Cl minus. And we would normally, Cl minus is a strong, it's a strong nucleophile, but because of the resonance structures of the O, when this leaves, there's an O minus here, that tosylate group this whole tosylate group is such a good leaving group that any halogen will come in and kick it off, including iodine. It would come in and easily kick it off. So stereochemically, what we can do is we can do this reaction and retain, invert, or go 50-50. But our goal here is to convert the OH into a better leaving group, and a leaving group that is compatible with our tertiary oxide or NH2 minus. So we got to convert it into a leaving group that's compatible with those negative bases, with those strong bases. There's a whole mechanism where it basically, SOCl2 looks like this. So you can imagine in the first step of that mechanism that it's probably going to lose the chlorine and attach the sulfur to the oxygen, and then that group is going to make a good leaving group. So it adds the OH then becomes like this, and then with the oxygen. So then the chloride you just lost can then come in and attack that sulfur and then like kick the whole group off. So it retains the configuration that way. The book does a better job in going through the details. I would just like you to remember it retains. Now, what about Pcl3 and Pcl5? I believe that in some books they cover it, in some books they don't, because I think there's a little bit of controversy. Because some books say it's retained, some books say it's inverted, and so this book doesn't mess with it. So Pcl3, Pcl5, probably write anything down, because you could find a book to justify your answer. So I kind of condensed this down. This was again something that was left over from last Thursday that I kind of condensed down here into the bare essentials. So we'll do more of the problems like this. So tomorrow then, for your reading, if you didn't read about Williamson ether synthesis, we're going to do that, because tomorrow is mostly about epoxides, which you just did. So we'll skip the epoxide, or we'll kind of leave the epoxide stuff, and we'll talk about ethers tomorrow, how you make them, and then the other thing you'll see for tonight is you'll see the basics of how to do free radical halogenation and that mechanism, which we'll also do tomorrow. Okay? So that's what you want to read, watch the video, and we'll do problems with that tomorrow.